Good afternoon. Today I would like to share a high-level overview of work conducted by the Oregon Department of Fish and Wildlife's Shellfish program, evaluating the potential of uncrewed aircraft systems, or UAS, for mapping seagrass in Oregon estuaries. One of the most important habitats in Oregon estuaries is the eelgrass Zostra marina. This plant grows in extensive meadows that create structured habitat for juvenile fish and shellfish and are an important ecosystem within Oregon estuaries. Many of the bivalve fisheries that ODFW manages utilize eelgrass beds during their life history. In addition, eelgrass is considered essential fish habitat by NOAA Fisheries and a protected habitat by the U.S. Army Corps of Engineers. They're a species also listed in the Oregon Conservation Strategy. Thus, any activities that impact eelgrass beds are regulated by federal and state agencies in Oregon. Because of the ecosystem services that eelgrass provides within estuaries and impact on managed fisheries, eelgrass is one of the major habitat components included in ODFW estuarine resource surveys. I lead the Shellfish and Estuary Assessment of Coastal Oregon project, or SEACOR. Among the project mandates is to generate eelgrass and other habitat distribution maps for the state based on our field surveys. One such example is shown here for Tillamook Bay. Within the Shellfish program, these maps and associated data are used to better understand Clam habitat associations, both to manage fisheries and to conserve habitats important to shellfish. Another example of how these eelgrass maps are used are during the review of permits for development projects in estuaries. These habitat maps are made available through several web mapping resources managed by the state, so these estuarine resource maps can also be used by county and city planners and other state agencies to manage estuarine resources. However, there are some limitations with these maps. First, the data is both time and labor intensive. The data for the map shown here required 3 years of fieldwork to generate. Second, these maps have low spatial resolution with cells ranging from 9 to 30 meters for estimates of the eelgrass population distribution. And most importantly, repeat surveys of estuaries occur on a decadal timescale relative to eelgrass population dynamics, which occur on seasonal and annual timescales. Because of this, we've been exploring methods to fill the spatial and temporal data gaps in our current eelgrass mapping efforts. The primary goals for our UAS project are to evaluate the potential of this technology for eelgrass mapping to supplement our field surveys. We also wanted to improve the spatiotemporal resolution of eelgrass distribution relative to the field surveys, and to develop workflows to track rapid changes in eelgrass to be able to respond to events such as marine heat waves and emerging management issues. We are developing our use of UAS in a framework that develops best practices for use of the technology in Oregon estuaries, an understanding of the trade-offs and limitations of UAS, streamlining data processing, and whenever possible, integrating UAS flights with field surveys to have synchronous data for the 2 types of data sources we collect for eelgrass populations. We have focused our UAS efforts in 2 bays along the North Oregon coast, Tillamook Bay and Netarts Bay, which are about 75 miles west of us on the coast. These bays have had extensive Zostra marina beds for at least the last 50 years. Both bays support important intertidal and subtidal recreational and commercial clam fisheries, and are also the major bays for oyster aquaculture along the north coast of the state. The maps shown here identify the classified eelgrass distributions for the 2 bays in blue. Note that one of the differences between the 2 bays is that Netarts Bay on the left has both the native Zostra marina and the non-native Zostra japonica, which has expanded in many Oregon bays since the early 2000s. Areas we have flown a UAS are indicated by the yellow polygons in both bays. The talk today will focus on results from a small 2.5 acre site in Netarts Bay, which was the focus of our initial UAS work in 2016 to 2019, in an area in the northwest area of Tillamook Bay, an area we call Bay Ocean, where our recent flights have occurred. Elements of a good UAS survey design can be subdivided into a planning component, field data collection, and data processing after the flights. The planning component includes identifying appropriate platforms, resolution needed, and flight plans to achieve your project goals. The field data collection component includes the UAS flight images, along with the ground control points and ground truthing data also collected with the flights. And finally, the data processing step includes all of the processing needed to go from the imagery collected by the drone to the final classification map products to address the research questions. Earlier, I mentioned that ground control is important for any UAS survey since it decreases the errors in geolocation of the final orthophoto that are used for classification. One of the challenges in estuaries and tide flats is the lack of permanent markers that could serve as ground control without deploying additional ground control on flights. We initially deployed ground control points on each of our flight days, but these deployments were labor intensive, took valuable low tide time away from the flights, and disturbed the study area which showed up on the final images. Our solution was to develop floating ground control points. We worked with a local sign company to develop GCPs made out of high-density urethane. These could be mounted on PVC posts in the field. The posts and ground control points can be deployed via foot or boat during the intermediate tides or other days that we don't plan to fly, and that they can be in place for multiple days before needing to be removed. This increased the efficiency for flight days since all the available low tide time was then available for the collection of imagery. Ground truthing is another important component of the UAS field surveys. These data are used to aid in the classification of produced imagery and to assess the accuracy of the final eelgrass maps. Ground truthing is typically done using ground surveys, and we've used two different types of approaches for our ground surveys. For new areas we're flying, we randomize ground truthing sites across the planned flight area. And secondly, we've also started to integrate our UAS flights with our ongoing field surveys, since the vegetation data from these surveys can be used without the need for additional sites sampled for the UAS flights. The map here shows one of the 5 UAS regions for Tillamook Bay, Bay Ocean North that I had mentioned earlier. The map on the right overlays SEACOR field survey points in this region, which include both systematic sampling in a 100 by 100 meter grid, along with a subset of randomized sites that are part of the SEACOR survey design. Here the points are identified as ones where seagrass was present in blue and those that lack any vegetation in brown. So let's transition to some of the products of our UAS flights. These maps here show a 2.5 acre region of Netarts Bay, which we flew from 2016 to 2019. Note that the resolution of the drone-based map here is around 6 millimeters for these low altitude flights relative to the meter to decimeter scale of our field surveys. Low altitude, high resolution flights were the approach we initially used as we were developing the UAS methods at this site. We did a supervised classification incorporating ground truth data, which identified habitat classes for native and non-native eelgrass, as well as 2 algal classes from these flights. As I mentioned, that we had flown this area multiple years, so we could also start to look at annual dynamics in eelgrass. One example is shown here with a 2016 classification on the left, and the 2017 classification on the right. Here, eelgrass distribution is combined native and non-native species in blue. There's not a major change in overall area of eelgrass in the region, but there have been shifts in the overall distribution. If we zoom into the Northeast region and overlay the classification for the 2 years, we can visualize this change. The 2016 distribution is in dark blue, and the 2017 distribution in light blue. This shows a 10 to 15 meter shift in the bed extent in 1 year. A big takeaway from this aspect of our UAS work is that it seems to capture the spatiotemporal dynamics that we are hoping to incorporate using this approach. I'd like to finish up with a quick look at some multispectral data that we collected this past summer. The map here is the Bay Ocean North imagery I've shown previously, but I've zoomed into the 3-acre area outlined in yellow. This was one of several areas that were flown using a multispectral camera system in 2023. The raw multispectral imagery was processed with an algorithm based on a modified SAVI index utilized for classifying eelgrass and aerial photographs in Oregon and other West Coast estuaries. This approach shows good promise for classification of vegetation. We did a quick check on this classification using our ground truth data within this 3-acre area. If you look at the field collected data or site photos, there's a strong coherence between the classification and ground data. You can see areas with continuous dense eelgrass, patchy edges, and unvegetated areas that all seem to match the classification that we used using this approach. We plan to do more detailed evaluation of the multispectral camera system over the next couple of years to refine how this can be applied to our mapping efforts. So in summary, UAS can be a powerful tool that complements ongoing ODFW research and monitoring programs in estuaries. From these surveys, we're now able to produce high-resolution habitat maps and track spatiotemporal dynamics of eelgrass on relevant scales for this resource. The multispectral imaging systems we've begun testing also show the potential for rapid vegetation mapping. We have already used drone imagery as a rapid response tool to address emerging resource management issues such as permit reviews for development projects and shellfish aquaculture. And currently, ODFW is working with other groups along the West Coast using UAS to map eelgrass, to share information, and develop best practices for applications of this technology on the West Coast. Thank you. Feel free to contact me if you have any questions.